All right, good morning, everybody. A couple of logistical things before we dive in here. First of all, if you're staying in the dorms, you need to check out by 1 p.m. this afternoon at the conference office. So if you haven't done that already, I suggest doing it right before lunch. And you're welcome to stash your bags and things in here. I can lock this room over lunch, so you can leave things in here and then take them with you when you leave later. The plan for the morning is Sandra's going to give an overview of some of the case studies and applications of Scenic that we've done in the past. And then most of the morning is devoted to short talks by users and potential users of Scenic from all sorts of different domains, academia and industry. We'll have a coffee break in between those two sessions. And then that will lead directly into our working group meetings. We'll have two parallel sessions. The autonomous driving working group, which has been meeting for about a year, will be in here. And of course, anyone is welcome to join that. And then I will be in the breakout room, the classroom, and the other Zoom link for the robotics and other domains working group, which we're just getting started. And the goal of these meetings is really to discuss applications of Scenic in those areas. What can we do to make Scenic more useful to people working in those areas, more accessible, et cetera, as well as monitoring progress that, within the Scenic project and outside on things that are work that's being done that's of interest to people working in those areas. So then we'll have lunch, and then we'll have, after lunch, whoops, go down here.
I think one more thing to mention
is
yeah, we'll have a group photograph during the coffee break, probably towards the end of that coffee break, a little bit before 11 o'clock. Okay, so don't wander away during the coffee break because we'd like to get a full group photograph.
Right. Then this afternoon, Eddie is going to give a presentation on using a companion tool to Scenic, Verify, and some more advanced applications of Scenic. We actually talked about generating synthetic data yesterday, so we may not do that again. And then we'll have our last hands-on lab session for you to get some experience actually working with Verify, using Scenic as part of a broader pipeline for running experiments and so forth. Then we'll have our last coffee break. And finally, we have an hour set aside for just general discussion based on everything that happened in the workshop, and maybe coming back with some things from the working groups that might be of interest to everyone in general, just talking about the future of the Scenic project and directions we're going, et cetera. Then we'll have a brief closing, and we'll give you some time at the end to fill out a survey about how the workshop went for you. And we really appreciate your feedback on that to help us improve for next time. Okay, so with that, I will turn it over to Sanjit for his presentation.
Okay, great. Good morning, everybody, and good day to everybody online. This morning session is more of a session focused on applications, including industry applications of Scenic. And what I'd like to do in this talk, which is going to be just about 15-20 minutes, is give a little bit of, again, a somewhat historical perspective on applications of Scenic. And I want to start out by recalling what I said yesterday morning, which is that what we really like to do is not just create single point tools for improving the state of art in AI-based autonomy, but we want to essentially create this design flow, an ecosystem of tools that can all talk to each other. And that's really one of the things that's motivated the Scenic project. So some of the things that we and others have already done, I've been addressing various steps in the tool chain that I show over here. So I'll start at the top with modeling and high-level design. So this is essentially the kind of thing that you can do when writing a Scenic program, which is you're modeling your view of the world in which the system is going to operate, and any assumptions that you have about it. Also, assumptions about the system itself. And then once you have that model, you typically, if you want to do verification and validation, you need to specify requirements that the system must satisfy. Classically, these requirements tend to be these safety and liveness properties that I'm sure many of you have learned about. But for autonomous systems, requirements tend to be more complicated. And we'll have one of the talks this morning talk about multi-objective specifications that you need to handle in this domain. And then I mentioned, the various steps like fuzz testing and falsification, as well as different types of formal verification. And all of these require a model like Scenic, an environment model, to be used as a basis for testing and verification. So this afternoon, Eddie's talk on Verify will touch upon these and how you can do these with Scenic. Then you want to do, once you find errors, failures, you'd like to do debugging and triage. And also, if these failures have been found in simulation, you want to be able to check whether they can actually occur in the real world. You want to do some sim to real validation. So that piece of it is also enabled by Scenic. You can do things like querying sensor data with Scenic programs. You can resynthesize your AI models and retrain. Some of this is done using data augmentation. And then this all ties in again to real world testing and runtime monitoring while the system is in operation in the real world, and dealing with things where you have to fall back to different safe controllers. So all of these steps, right? These are all steps in the design flow. And it's really cyclic, because once you find a problem and you want to re-architect your system, you start back by adjusting your models. And so what we've tried to do is to architect the Scenic and Verify tools so that hopefully they are usable and interoperable with other tools as well. Okay, and we want to be able to develop this open source ecosystem. So in the remaining time I have, I'm going to actually present one. Perhaps I'll have time just to talk about this one. So this is a project that we did now more than 5 years ago in collaboration with Boeing. And so it's from a Scenic modeling perspective, it's pretty simple. But I think it's a nice example because it shows how you can do multiple steps in the design flow. And so this particular problem was a challenge problem posed in a DARPA project where Boeing was charged with presenting challenge problems, and they came up with this example called TaxiNet. So TaxiNet is a system that this Boeing R&D group designed to use deep learning for autonomous taxiing of a plane on a runway. And basically the setup was that if you can look at the right-hand side here, there's a plane and there's a camera mounted on the right wing of the plane. And this image is an image taken from that camera. And that image goes into a neural network, which is TaxiNet. And the job of this neural network is to produce something called the cross-track error estimate, CTE estimate, which is an estimate of how much the nose of the plane is deviating from the center line of the runway, right? So as it taxis down the runway, the nominal behavior is you want it to be aligned with the center line. Okay, so the deviation is the error that goes into a conventional controller, which will then actuate the steering and throttle based on that. And so if everything is going well, this is the operation of TaxiNet. So it's going down this runway. It is in a simulator called X-Plane, which Scenic has an interface to. And in spite of these skid marks on the runway, you still see the plane doing a reasonable job, right? Or TaxiNet doing a reasonable job of keeping the plane on the center line. All right, so the question that was posed is, can you find flaws in this particular system? And then can you improve the system so that it becomes safer? Okay. And so we went through many steps in the design cycle. So first we modeled different runway scenarios using Scenic. And this was based on conversations with the Boeing team about what the expected operating conditions look like. Then we specified the safety property, which was in temporal logic. And then we ran falsification to find scenarios, concrete scenarios, where the system violates its safety specification. And then once we find these kinds of scenarios, we wanted to have a way to do debugging to root cause and find what what's the core issue with the system that's leading to these failures. And then once we understand the failures, we wanted to use those insights to retrain the neural network and make it safer. And then iterate this. And then one more piece that we added, this was added a little later in 2022, is an approach that adds runtime assurance, meaning that this TaxiNet is designed for a particular scenario modeled in Scenic. But what happens if the real world deviates from that scenario? So you need to have a fallback option there, and that's what runtime assurance is. Okay, so here's the Scenic program. If I can go back. Let's see. There we go. Here's the Scenic program for the scenario that Boeing told us, which was, as I think all of you are proto-Scenic experts by now, if not Scenic experts. And so they basically told us that the initial condition is all that changes. That's the time of day, whether there are clouds in the sky, and what type of clouds there are from the weather report, whether there's rain and how much rain there is, and the initial orientation and the position of the plane on the runway. And so you basically see all of those things modeled in Scenic with associated distribution. So I won't go through the program in detail, but it basically fits on a slide. So it's a pretty simple model. And then the next step is specify the safety condition. And the safety condition is specified in temporal logic like this. So what this means is that sometime during an initial phase of 10 seconds, between 0 and 10, the CTE falls below 1.5 meters, and it stays there throughout after that. Okay, so after that point, for the rest of the operation, it stays within 1.5. So the way falsification works, and several of you know it, is that we take this temporal logic property and we turn this into a cost function. And then you have to minimize the cost function. This is what verify does. And verify has many algorithms. In fact, several of you are working on falsification algorithms, and those can be integrated into verify. So that's a topic for this afternoon. But if you try to minimize the cost function and you drive the value below 0, then that leads to a safety violation. And what we found in this case study is that out of about 4,000 automatically generated simulations, 45% of those violated the property, and 9% were really bad violations in the sense that the plane left the runway entirely. So here you see an example of one such. It's early morning, light rain, and kind of dark conditions, and TaxiNet has lost the center line and is proceeding to drive the plane off the runway. Okay? So that's an example of a failure scenario. And as you can see, there were about 2,000 of these failure scenarios, right? And so the obvious question is, what happened? What went wrong? What were the flaw in TaxiNet that was leading to these failures? And this is where there's a feature of verify, which you'll also learn about this afternoon, that came in handy. And what this feature does is it's very simple. It takes all the counterexamples that it finds, and it also takes all the correct executions, and it organizes that data into a table. And that table is organized based on the variables in the Scenic program, with the semantic features of the environment. And then we can look for correlations. One particular correlation we found was sensitivity to time. So if here, what this plot is showing is time of day on the x-axis from 6 a.m. to 6 p.m. And on the y-axis, it's showing the value of this cost function. And if the value is below 0, it's unsafe. And if it's above 0, it's safe. So you can see here that in the early morning hours, it's unsafe. Okay, the median value. And then mid-morning, early afternoon, most of the time it's safe, but mid-afternoon, again, it dips below 0. And then again in the evening. Okay, and we saw an example of what's happening in the morning, dealing with low light. But we were pretty puzzled about the afternoon till we looked at the images. And if you look at the right-hand side image, you can see the shadow of the plane's wings on the runway. And especially in clear conditions, cloudless skies, it was actually the shadow effects were pretty prominent, and that was what was throwing off the neural network. And so this is a way of using these formal methods to identify limitations of a training data set and biases, which you can then rectify. And so that's what we did using Scenic. So we essentially created a Scenic program that was designed to generate data, images in this case, that covers these scenarios, right, that TaxiNet was not good at. And so we call it Scenic guided retraining. And then after that retraining, we found that the neural network behaved much better. So here, exactly the same environment conditions. You can see the original neural network on the top is driving the plane off the runway, and then the retrained TaxiNet is more or less keeping it on the center line, right? And you can also see this quantitatively. So, if you look at again, the same plot, the blue points and the blue curve, the median value is above 0, right? So it's safe much more of the time. Okay, and then the final thing I mentioned was this runtime assurance aspect. So this is great. You have your Scenic scenario, and we can actually not only do falsification, but we can do what is called a statistical model checking. And that can give you a probability that the system is safe. Because you can say the system satisfies this property with probability 0.9999, right? And maybe that's good enough for you. But still, there's the small 0.0001 probability that something can go wrong. And furthermore, all the guarantees are with respect to that Scenic program, right? So what happens if in actual operation, the environment is different? And this is what we did in subsequent work. So there's work where we used an architecture called Simplex, and so this video is going to show what happens here. So we take the Scenic program and we compile it into a runtime monitor, and the runtime monitor operates over a subset of the sensors that you trust, and it monitors the scenario with some look ahead. So it's looking for an environment. So initially it says trusted environment, but it's constantly monitoring the environment parameters. And if it thinks that it's going to deviate from the Scenic modeled environment, it'll put an alert up there, and then it will it will turn over to a safe fallback controller. So which is what it does over there. So seemingly if you had looked at that video carefully, there was a small drift that was happening to the right, but the controller was able to, the runtime monitor was able to catch that with a look ahead, and then switch over to a safer controller in time. So you can do this to kind of switch between mostly safe and high performance controller with much more provably safe but lower performance controller, and then you can architect the system using Scenic. All right, so I don't think I have time to talk about this other case study that we did, but I did show a video yesterday morning, and I'll just mention it very quick. The other one was in the autonomous driving domain, and a lot of the use cases of Scenic that you saw yesterday were using it in simulation, right? And there's always this question that if you find a safety violation in simulation, if you find problems in simulation, do they really transfer in the real world, right? And secondly, the next question is, can we use simulation tools to actually design real-world tests so that you use your real-world testing infrastructure more efficiently, right? Because you don't have, it takes a long time to set up these tests for road testing or on other physical environments. And so you can only do a certain limited number, and you want to use that budget very optimally. So those are the two questions that we wanted to ask in this particular case study, and we worked with American Automobile Association, which operates one of the big autonomous vehicle testing facilities in the Bay Area. And so I'll just skip over, but the gist of this is we modeled a scenario in Scenic, which had to do with a car and a pedestrian crossing. And I'll show you what that scenario is. And this is actually it's a particularly the scenarios of vehicles interacting with so-called vulnerable road users is a particularly critical domain for us to apply this technology. And so this particular scenario was this case where the autonomous vehicle is starting at this blue dot in this bottom right corner, and it has to navigate to the blue dot up there on the top right. But there's a pedestrian crossing in the way. And the way we model the pedestrian behavior is the pedestrian starts at the yellow dot and has to cross over to the red dot. But the pedestrian is going to hesitate in the middle of the crosswalk for a period of time. And all of those things were randomized, like when the pedestrian starts walking, where they stop, how long they hesitate, etc. Using Scenic. Okay, so we found issues in simulation. And that's visualized here, and I won't go over the details. But then the question was, do these actually happen in practice? And what we found was that if we found something that was unsafe in simulation, it was a majority of the time also unsafe on the road. And unsafe just meant that the car got too close to the pedestrian. So collisions, of course, are really unsafe test cases, but other ones where the car gets within the middle of the car gets within like 2 meters of the pedestrian is also unsafe, right? And what we also found was that if it was safe in simulation, it was a large majority of time safe on the road. And then here is one of the cases that I showed yesterday that we saw something that happened in simulation where the car hit the pedestrian as the pedestrian was crossing. And then we saw this replicated on the road. And in particular, if you look a little closely at this particular video, you'll see that I can replay this. Yeah, so the pedestrian dummy starts crossing, and then the car comes up on the turn, and you'll see that the car actually slows down and stops. So it actually sees the pedestrian dummy and then decides to drive into it anyway, right? And then we wanted to debug this, and we went and visualized this. This was using a version of the Apollo software, Baidu's Apollo software. And this is from the viewpoint of the Apollo visualizer. So you see the autonomous vehicle coming up on the turn. You see that fence where it knows that it has to stop. That's its destination. And you see the yellow box. Well, that's the pedestrian. So it detects the pedestrian. It puts the fence even. And then at some point, it loses the yellow box, right? And then it drives into the pedestrian. So that's what happened over there. All right. So with that, I think I'm at the end of my time. So let me just finish up here. So yesterday you learned about many different features of Scenic, which are all listed here on the left. There's also many use cases of Scenic, and some of them you've seen and some more you will see today. So we talked about data generation yesterday. We talked, of course, about using Scenic to generate simulation tests, which is also a form of fuzz testing, because you can think of the Scenic model as your fuzzing constraints. We haven't talked about requirement specification, so we'll have at least one talk about that today. We'll also hear about falsification and verification. I mentioned debugging and triage a little bit. I don't think we're going to have a talk specifically on that more, but I think we're happy to talk to people who are interested in that offline. Data augmentation. You can do parameter synthesis and training, and you'll hear a little bit about reinforcement learning applications today. I talked about runtime monitor generation, sim-to-real validation, training RL agents. I mentioned training people in virtual and augmented reality. You'll hear about that as well. Okay, so there's many different applications, but I think there's several more that the community has also investigated, and we hope to hear about that as well this morning. Okay, with that, I will stop here, and then let's switch over to our presenters. So let's see, is Ali Nouri there? Okay. We could go straight to Alex. Yeah, why don't we do that? We'll go straight to Alex. And so, yeah, I can stop. And while we're switching over, I'm happy to take any questions.